Hello, everyone. I'm Jordan, and this is my creative assignment. I kind of came up with this dynamics problem focused on a spacecraft with some um, rigid elements, kind of moving, and so I'll kind of dive into it. So essentially, I have this spacecraft. It's in a torque-free environment, so generally angular momentum is conserved. It has two deployable solar panels on the left and the right. You can see they're kind of symmetrical here, and yeah, those solar panels start kind of in like a upright position vertically, and then they rotate down, and then so I have these four thrusters, and the problem statement is essentially the bottom left thruster at some point, like, bursts, and so that imparts some sort of momentum, impulse. Some questions associated with that. For example, what is the initial angular momentum of the whole system, and what is it after the thruster bursts? And then what angular accelerations can we observe in the left panel, the right panel, and the spacecraft body? And that's like angular acceleration and sort of translational for the spacecraft body, because the panels are constrained in that sort of frame. So those are the first questions I wanted to kind of analyze here. So I have some initial conditions that I came up with. So initial conditions for XY position of the spacecraft body, and then the orientation of the spacecraft body, orientation of each solar panel, and relative to like the inertial horizontal, and then initial angular rates, as well as different lengths, masses, and the impulse of that sort of thruster burst here as 0.2 kilogram meter squared. We'll kind of get into the additional conditions a little later. So the first problem was, what is the initial angular momentum of the system, and how does it change after the thruster bursts? So the first thing to do is calculate moment of inertia for the spacecraft body and the solar panels. So we'll use this 1/12 L squared plus W squared formula times the mass. So here we have like the spacecraft body mass, and then the spacecraft body length and width. So we can do that for the spacecraft and for the panels to get those values. Seems I flipped them. So the spacecraft moment of inertia is 13.66 kilogram meter squared, and then for the panels it's only 0.33 kilogram meter squared, which tracks because they're kind of much less massive, even though they might be a little bit longer. So the next thing we can do is use the angular rate and then the moment of inertia for each of those three elements to compute the angular momentum. So here we do that for the spacecraft body, minus 0.2385 kilogram meter squared per second. For the left panel, 0.023, and for the right panel, negative 0.035. So based on initial conditions, this makes sense because in the inertial frame, even though both panels are rotating at the same kind of rate, the spacecraft body is also rotating. So when you add those up inertially, they're rotating at different rates. So that's why you see this, that's why they're not just direct inverses. So to get the the total angular momentum of the system, we can just add those up, and we get this value minus 0.25 kilogram meter squared. So the next thing is, how does this change once the thruster bursts? Pretty simple. We know that the change in angular momentum is equal to sort of any moment, and so if we're looking at over some like small horizon, we can just say that's an impulse, or an angular impulse actually. We'll calculate that just using the actual impulse and then kind of the moment arm that it's acting over, and so we get this value JT. With the initial conditions and the initial angular momentum, we can add those to the initial angular momentum and then the angular impulse to get the final angular momentum, since that'll be conserved in this kind of torque-free system. And this is what we get. So that's that. Then the second part is problem B, which is more interesting probably, but essentially we're just trying to get the angular accelerations and the translational accelerations for the spacecraft body and then each of the solar panels when we get this kind of impulse force. So let's see. This is my free body diagram. We have X defined to the right, Y defined up for the solar panels, and then inverse for the spacecraft body. So first we'll define the constraint equations. Much like homework 3, we just have them for x, y, and for the left panel, x, y for the right panel. But clearly they're a function of the solar panel x, y positions, and then the orientations of each panel and the spacecraft. So we'll differentiate these equations twice in order to get equations with second order terms that we can combine with the dynamics equations into a big matrix or set of matrices and solve that way. This kind of gives us 4 new equations, or 4 extra equations. So that's what you see here in 011. And then, of course, we have the dynamics equations. So we have them for, x, y, for the spacecraft left and right panels, and then an orientation for all 3 of those elements as well. These I kind of just gleaned from the geometry. None of them are too complicated, but I did for now include like all of the elements. And this is this. You can see that there's like contributions from the impulse in both x and y, depending on whether or not the spacecraft body is tilted at all, which makes sense. So kind of by plugging in, or we can reduce these equations by plugging these equations up here, kind of these ones, and down here for these 4, and that just simplifies our matrix, makes it so that we don't have states x, y for the left and the right panel, and it simplifies everything. So so that's what I've done down here, and these are kind of just the terms that are a function of these second order states that we're trying to solve for. And then on the other hand, we have the terms that are constant, which are not kind of linear combinations of those second order functions. So some contributions from the impulse, angular impulse, and then down here from those constraint equations, we have we end up with some quote unquote constants. So I tried to test this first with sort of a more intuitive initial set of initial conditions where we just have a symmetrical system where it's horizontal. The left and the right panel are just 30 degrees up from the horizontal, and they're rotating downward. And so I wanted to see that everything kind of checked out and that the values were matched my intuition and were symmetrical. So this is what I ended up seeing. No acceleration in x is good. You wouldn't expect that for this like symmetrical system. No angular acceleration for the spacecraft body, inverse angular accelerations for the panels, and opposite their rotation rate, which means they're slowing down. And then we see the x forces cancel out, which makes perfect sense. And then the y forces act in the same direction, which I would also intuitively kind of guess that. And so those are positive, and we see that the acceleration in y is negative, so that makes sense as well. So that's perfect. So I felt kind of encouraged to move on to this more complicated scenario, and these are the results for that. So you can see that with this impulse, most of it is directly mapped to sort of the y acceleration, which makes sense. It's a cosine of the spacecraft orientation. So most of it will go to y with a little bit to x. We see that there's a pretty strong negative acceleration for the spacecraft body. Also makes sense because it's a positive y force and the moment arm is kind of negative. So that's what will happen. And we also see that the left panel actually ends up kind of getting jerked pretty quick and accelerating. Whereas the right one, this is actually not accelerating it because it has a negative rotation rate. So this is slowing it down, which is pretty neat. I think you'd expect that if you push the left side and the left one's spinning down, it'll kind of jerk it down faster. Whereas the right one, on the spacecraft will kind of catch up to that panel and it'll feel slower. So I think that's what we see here. And that's sort of what I wanted to talk about, and hope you enjoyed it.